Now we'll discuss the skeletal muscle microstructure sliding theory. For the microstructure of skeletal muscle, also called myofibril, there are some key points. And for the enlarged one, there are a few very key structures that include thin filament and thick filament. For the cross-section, there are I band, H zone, M zone, and the outer edge of A band. Let's see the details of microstructure of skeletal muscle. The first thing is sacrotabular system, called transverse tubules. It is a part of muscle cell's membrane, and it can conduct action potential to muscle cells deeply. It's very useful for action potential transmission. It also has longitudinal tubules, also called sarcoplasmic reticulum, SR. There are junctional SR, also called terminal cisterna. It stores large amount of calcium, release calcium and reabsorb calcium ions. Triad tubule. There are two terminal cisterna and one T-tubules. It's a basic structure of excitation-contraction coupling. The key point is calcium ions. It's a key material. Let's see this picture. As we talked before, the myofibrils include thin filament and thick filament, and there are triad and sarcoplasmic reticulum and sarcoluminar and sarcoplasm. The myofibrils include thick filament and thin filament. For the thick filament, there's myosin, and for the thin filament, the structure includes actin, troponin, and tropomyosin. The thick filament, also myosin, is a bundle of myosin protein shaped like double-head golf clubs. The myosin head can make cross bridge, have two binding sites, actin binding site and ATP binding site, which got the energy from ATP nates. ATP provide energy to generate power stroke to get the myosin head move around an axis. Let's see the myosin in details. The thick filament, they have myosin tails, has myosin head, which called cross bridge, make the cross bridge. The thin filaments include actin, tropomyosin, troponin. It connects in the Z disc, and there's troponin and actin molecule, which can connect for the thick filament head to make movement. And this picture is very clear and provides more details. The most important content of this class is a sliding theory. The sliding theory, the key step is that myosin, which make cross bridge, is binding actin combined with actin reversibly, and the cross bridge swell and thin filament sliding, sarcomere shortening by 100%. Now let's see the steps of sliding theory. And step 1, the first step, is exposure of active site. And for step 2, the cross bridge, that means the head of thick filament attach the active site. And step 3, the pivoting of myosin head. And step 4, after the rotation of the cross bridge detached from the active site. And for step 5, the myosin inactivation. Let's see the image of the filament movement. You see the D zone is in the center of the sarcomere, and the actin move inward, and the length gets shorter and shorter and shorter. It's quite not very difficult for the. And let's see the excitation contraction coupling. The process coupling the action potential with the mechanical contraction. The process in details as follows. Action potential conducts along the T-tube to calcium channels and the junction SR membrane ryanodine receptor combined, and the GSR calcium releasing and the calcium binding to troponin, moving troponin myosin, exposing the myosin binding site on actin, then caused the sliding contraction, and then reabsorbed by the GSR membrane calcium pump. The calcium ion concentration decreased again, and the muscle relaxation. See some picture in details show us the calcium releasing during excitation contraction coupling. This is, I think, the first step, and then the receptor binding caused the calcium channel open, and the calcium flows out SR into cytoplasm, and the calcium channel closed when action potential ends. The active calcium continually return calcium to SR. So the excitation contraction coupling key material is calcium. The calcium ions decreased the excitation contraction decoupling. Excitation contraction basic structure is triad tube structure. The affecting muscle contraction performance factors. I think this is the after excitation effect. After the excitation, the contraction characteristics. The performance include the force and shortening of the filament. There are two types of performance: the isometric contraction and the isotonic contraction. The isometric contraction is the length not change, the force change. But for isotonic contraction, the force not change and length changed. In the first line, the muscles contract and then they pull the substance up. So in this process, the strength equals the 3 kilograms gravity, and it's constant, but the lengths are shortened. This is isotonic contraction. And for the other one, let's see, the gravity is pretty larger. The contraction did not pull the substance up, so the length did not change. It's isometric. The thing changed is the power, the tension. So it's the two type is quite different. This is the theory, the basis of theory, preload and afterload. So let's see the effect of preload. The concept of preload is the load encountered by the muscles before it begins to contract. Preload influences the muscle initial length. So there's a key point: initial length, the length-tension relationship. There is an optimal preload, optimal initial length. That means the sarcomere equals to around 2 micron. The muscle tension is got the biggest, the cross bridge number maximum. Got the biggest tensions, the biggest power for the muscles. Let's see the different preload and the different initial lengths, how the initial lengths affect the tensions. Let's see the curves, the point, the highest point. In this picture, we see at the best initial length, there's more cross bridge is active. So this causes maximum of power, maximum of tension produced. The effect of afterload. The concept of afterload is the load encountered by the muscles after it begins to contract. Afterload influenced the force and velocity of muscle contraction. The force-velocity relationship: if the afterload is 0, the velocity got V max, and the afterload equals the P0. That means without any length change, there's no velocity. The velocity is 0 and there's no work produced. The afterload is equals P0. So the velocity is in direct proportional to cross-bridge cycle. The afterload increased and the cycle increased, the velocity decreased. And the force is also proportional to the cross-bridge cycle number. The afterload increased, the active cross-bridge number increased, and the force increased too accordingly. Now let's see the factors that affect the muscle contraction. The intrinsic property of muscles determining its performance being independent of preload and afterload. The calcium is the most important thing that affects the contractibility. Epinephrine, caffeine, will increase the contractibility. Let's move to the summation of the muscle contraction. The motor unit summation, that has spatial summation, its size principle, and the frequency summation, its temporal summation. There's a twitch. There are two kinds of contraction, the frequency summation. A twitch, a single contraction, and tenderness. It's incomplete tenderness and complete tenderness. Let's see the difference in picture. As we know, the action potential lasts 1 to 2 milliseconds, and the contraction can last up to 200 milliseconds. The twitch is one stimulus and causes an action potential of the muscle and one contraction of the muscles. The tenderness means a number of stimulus, many action potential of the muscles, and many contraction summations. It is incomplete or complete tenderness when there's no relaxation of the muscles between two muscle contractions. In the first line, the picture shows us incomplete tendinous contraction. There's a summation of the contraction powers. We got more powerful contract. In the second line, we got tendinous, complete tendinous contraction. If there's 1 second, 1 per second, we got the left one, and 5 per second, we got the middle. Frequency increased continually to 5 per second. That means 50 hertz. We got totally complete tendinous. So the contraction switch from twitch, 1 stimulus per second, to tendinous, 50 stimulus per second. From twitch, incomplete tendinous, and complete tendinous contraction. That's all for today.